In this video, I'm going to talk about something that I've never ever really talked about before on this channel, and that is the subject of organic chemistry, which is totally random and totally different to any of the self-improvement content that I've ever produced in the past. But I'm good at it, I enjoy it, and so I might as well give away my knowledge to those who seek it, and maybe I'll end up somewhere. I'm hoping that this can be the start of a series, which I seek knowledge and I just produce these, I don't know what you call it, PowerPoints and all that sort of stuff, and maybe you'll enjoy it. But yeah, this is an introduction of sorts, and hopefully, if you enjoy it and you understand what I'm trying to explain, then you'll stay for more advanced stuff. But organic chemistry, in its most basic form, is a branch of chemistry which focuses on the chemical reactions of carbon containing compounds. I'm going to kind of have to start from the very beginning. Now, carbon, as you'll see here, this little C is an element. And carbon is the base of all organic chemistry, and it requires 4 bonds. If you imagine these little lines here as bonds for a full outer shell, that is when this atom is most stable, is when it has 4 bonds. If it only had 3 bonds, it might be a free radical, it might be a carbocation. They are not as stable as just when it's pure and neutral and has 4 bonds filling up its outer shell. The base of all organic reactions and all of the nomenclature, by the way, it's quite a hard word to pronounce, is the naming of these organic molecules. You may have, I don't know, heard of all like the pharmaceutical drugs and all that sort of stuff, like your paracetamols, ibuprofen. If you imagine like the full, proper scientific name of those molecules with all the different like groups and stuff that it has, that is what nomenclature is, and all of that is based off of the simple carbon chain. You'll see here, this is a carbon chain where the carbons are connected to each other and they're fully saturated with hydrogens. When a carbon chain is fully saturated with hydrogens, it is known as an alkane, which is the simplest homologous series in organic chemistry. Now, a homologous series is basically just a group of chemicals with similar chemical and physical properties. The physical properties will normally either increase or decrease in sort of value, because a homologous series, you'll have maybe something like methane, which is just one single carbon, and then you add a carbon on every single time, and then you get to maybe 8, 10 carbons. That's what a homologous series is. It's the addition of carbons to an already existing carbon chain. Now, the basic nomenclature for organic chemistry contains some prefixes and some suffixes, and the most basic part is the numbering of the main base carbon chain. IUPAC is the Association International Union for Pure and Applied Chemistry, I think it is, create the rules for the naming of these molecules. And just like the chemistry itself, the nomenclature is based off of the carbon chain. If you imagine a molecule, say like this carbon chain has 8 carbons in it. This is the longest carbon chain in the molecule. Sometimes molecules can have things like branching and stuff like that. We'll get onto that in a little bit in further slides. But right now, this carbon chain has 8 carbons in it, and it is the longest carbon chain in this molecule. The prefix for 8 carbons being the longest chain is oct. And oct, you may have heard of things like, I don't know, oxygens before, but yeah, this molecule that you see here is called octane because the ane is what tells you that it is an alkane, a fully saturated hydrocarbon. That is where all of the bonds to carbon are either single bonds to another carbon or to hydrogens, basically. That's the kind of basic, simple nomenclature. Now, branch isomerism is where things get a little bit more complicated, I suppose. You'll see these 2 molecules here. These molecules have the same chemical formula, C8H20. This isn't C8H2O, it's C8H20. I guess the 0 looks a little bit like an O. However, this molecule here, you'll see, has branching. It has a carbon here that's, instead of being bonded to 2 other carbons, like it would be in a straight chain, it's bonded to 3 carbons. And that means that this molecule has branching. And even though these molecules have the same chemical formula, they have different physical properties, and this is known as isomerism. And branch isomerism is normally to do with just simple pure alkanes, maybe some alkenes and other stuff in there, but I'm going to go through this because I've not introduced you to any other functional groups and stuff like that yet, where things can get a little bit more complicated. But the way that these branched molecules are named is using more prefixes. And the prefix for a 1 carbon branch, like this single line here, is a 1 carbon branch. I might as well go through what these sort of lines represent, I suppose, because this is known as a skeletal formula of a molecule. This molecule here is the exact same as the molecule on the previous slide. It's just got rid of all the carbons and the hydrogens, which if you were drawing it out would be incredibly tedious, right? So this little thing at the end is a carbon. This 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 is a carbon. And this is a carbon. And this is a carbon. And even though it seems like they only have 2 bonds, you have to assume that if it's not got any other functional group on it, it's just saturated with hydrogen, basically. That's how these skeletal formulas work. But this one single line, it's not got any other divots on it like you would have, because normally when these carbons join together in skeletal formula, it forms a divot. This only has one single line, so it has one chain, and this is known as a methyl group. You'll notice the meth prefix is still there, but it's now got this little ill bit, which represents that there is some branching on the molecule. Now, to actually try and name this molecule, you can see the name here, 2,5-dimethylhexane. To explain where that name comes from, the hexane part comes from the fact that the longest straight carbon chain is 1, 2, 3, 4, 5, 6 carbons long, and the 2,5-dimethyl part is because if you count from left to right, or even right to left perhaps, 1, 2, 3, 4, 5, these methyl groups are on the 2nd and 5th positions of the molecule, and there's 2 of them, so you do it as dimethyl instead of just 2-methyl or something like that, because the 2 could then get confused for another methyl group on the 2nd position. Now, for instance, if there was another methyl group on this 3rd position, it would be known as 2,3,5 trimethylhexane, and if there was another one on the 4th position, it would be known as 2,3,4 tetramethylhexane. That's how these substituents work. If there's 4 of the same substituent on a molecule, it goes from just being nothing to di, tri, tetra. I guess there's maybe penta, hexa, and then you can like go up and up and up and up. But yeah, you'll see these other prefixes here. You'll have methyl, ethyl. If you had a carbon coming from there and then there, that would be known as an ethyl group because it has 2 carbons. If you had 3 going like there, there, then there, that's a propyl group because it's a 3 carbon branch. And these little pen things, it disappears after as well. That's actually really cool. Can't lie. This whole like thingy with the circle and stuff is actually really exciting me. I love how this thing works. But yeah, then you've got butyl and pentyl as well. That would represent 4 and 5 carbon chain branches, but you don't really need to go any further than that. To be honest, you're not gonna find like 5 long carbon chains unless it's a massive molecule. But yeah, let's try to name some of these molecules. Hopefully I've explained it well enough to you that you'll be able to maybe pause and try figure out how to do this on your own. You just count the carbon chain and look at the substituents, look at the numbers, and see if you can get the stuff right. But to name these molecules, if you count the longest carbon chain on this top molecule here, you've got 1, 2, 3, 4. That means it's going to have the prefix but. And it's a saturated molecule, so it's going to be butane. Now, this methyl group is going to be a prefix. But because it's on the 2nd carbon, it's going to be 2-methyl butane. Now, things like 3-methyl butane don't exist because if you moved it from this carbon to this carbon, you just then count from the right-hand side 1, 2, 3, 4 to make it still 2-methyl butane. It's the exact same molecule. That is because obviously if you just rotate the molecule 180 degrees, it just becomes the same thing. So it's not going to have any different chemical properties or physical properties. Therefore, it doesn't need a different name or a different sort of signalation that it is something different. But now onto this molecule here, which looks a little bit hard to grasp. Thankfully, it's got the sort of carbon chains numbered for me. I'm assuming this is probably from another website that's tried to explain organic nomenclature, but you're going to go from right to left because you want to make these numbers as low as possible, like you saw with 2 or 3-methyl butane. 1, you wouldn't have 3-methyl butane because it's just the same molecule, but 2, you just count from the other side to make the number as low as possible. You'll see most of these substituents are on the right-hand side, and the numbers when you count from right to left, when you add them up, are less than if you did it from left to right. So that's why we're going from right to left this time, but it can change depending on where the substituents are. So here you're going to count from right to left, 1, 2, 3, 4, 5. Pretty simple. Then you've got these 2 methyl groups, 2 and 4. That is then going to be 2,4-dimethyl, and you're then going to have the hexane at the end. Then on this 3rd position, you have an ethyl group, and that's because it contains 2 carbons in its branch. I think that when you name it, the methyl goes before the ethyl. So when this molecule, the name of this molecule is 2,4-methyl 3-ethyl hexane. It's such a mouthful pronouncing some of these words, and even though this is just basically oil, some of the nomenclature of these oil and branch molecules can be incredibly hard to pronounce and wrap your head around. But now, to go on to something different, alkene nomenclature. An alkene is a molecule with a carbon-carbon double bond, as you will see here to the right of me. Its appearance in a molecule is represented by the suffix -ene. Instead of it being -ane, like when it was an alkane, fully saturated with hydrogen, it's now -ene. And that is able to signal to you, if you are looking at molecules online, that this contains a carbon-carbon double bond. That's the reason why all this nomenclature exists. This molecule here is the simplest alkene. It is known as ethene. You'll notice 2 carbons and the prefix eth. The reason this is the simplest hydrocarbon is because you can't have a carbon-carbon double bond and only have 1 carbon. That just doesn't really work. The double bond being present here shows that this molecule is unsaturated. The carbons are not fully saturated with hydrogen. If you open this double bond up so that the carbon-carbon was single bonded, it would be able to bond to another hydrogen each once, and it would just be known as ethane and be a saturated hydrocarbon. But the double bond makes this unsaturated, and that can give it some interesting chemistry. That is why it is known as a separate functional group to an alkane, because it and physical chemical reactivity and physical properties. This double bond, for instance, though, was part of a bigger molecule. Say you've got the molecules on the other slide. Let me see if I can go back. Nope, that's the wrong slide. Let's try go back. Yeah, imagine you had a double bond. Let me draw it out. Maybe it would be good if it actually stayed this time. If you imagine this, that's a double bond. Just imagine that, even if it disappears, that is a double bond. That is going to be but2-ene, but-2-ene, because the double bond starts on the second carbon, and because the double bond starts on the second carbon if you're going from left to right. However, if there was a double bond maybe on the first carbon here, like imagine that's then going to be but1-ene, and when you add the methyl group, it's going to be 2-methyl-but2-ene or 2-methyl-but1-ene. But imagine the double bond was actually here. That then serves some interesting chemistry, because it's not 2-methyl anymore. It's actually going to be 3-methyl, because you're going to count from this double bond here, because the double bond takes priority when the numbers try to be as low as possible over the methyl group, so it's going to be 3-methyl-but1-ene. Now there's even more molecules here to wrap your head around. Now you're going to notice that there's a methyl group here and alkene here for this molecule. Because the alkene takes priority over the methyl group, you're going to name from left to right. 1, 2, 3, 4, 5. That is the longest carbon chain. You could technically name it 1, 2, 3, 4 and then go for this one as the 5th carbon, but it's still going to end up the same because this methyl group is on the exact same carbon as this one would be if the chain was labeled differently. That means that the prefix is going to be pent because it contains 5 carbons in its longest chain. Alkene is in the 1st position, so it's going to be pent-1-ene, and the methyl is on the 4th position, so it's going to be 4-methyl-pent-1-ene. Essentially, I probably should have written the names up on here, but it's fine. Hopefully you can kind of figure that out. Now, this molecule is even more complicated. If you want to try to figure out the name of that, then be my guest, pause the video, and I'll then explain it to you and you can see yourself how you did, essentially. So the longest carbon chain here is going to be 1, 2, 3, 4, 5, 6, 7, 8, counting from the right this time, because the carbon-carbon double bond is far closer to the right than it is the left. Because there's 8 carbons in this longest chain possible, the prefix is going to be oct, and because this double bond is on the 2nd position, it's going to be oct-2-ene, essentially. Then the 2 methyl groups, one is on the 2nd position, one is on the 6th position, it's going to be 2,6-dimethyl-oct-1-ene. That is the name of this molecule. Even though it's just a bit of oil, some of the namings of these molecules can be pretty complicated, as I said earlier. Now there's some even more functional groups. This is just a little bit of an introduction to immerse yourself in the complicatedness of organic chemistry, I suppose. But here you've got an alcohol, here you've got an amide. All of this stuff has some very complicated chemistry. You'll notice that alcohols has the prefix ol, and it can have the prefix hydroxy. The halogens, fluorine, chlorine, bromine, and iodine can also be involved in organic chemistry, and they have the prefixes fluoro, chloro, bromo, and iodo. All of these functional groups are complicated stuff that I'll talk about later. You'll notice amines, you'll notice that it can have the prefix amino. You may remember that from amino acids, and that's to do with like health and fitness and stuff. That's why organic chemistry can sometimes be slightly related to health and fitness, and that's kind of one of the reasons that I like it, because it can be linked ever so slightly to things I also love in self-improvement. The names of these molecules are also incredibly complicated. Here you'll notice that it has an alcohol, a methyl group, and an alkene. The alcohol being a more complicated, or it just takes priority essentially. This alcohol takes priority in the numbering, so the number has to be as low as possible. So you're going to count from this carbon here, which is the carbon this OH is connected to. So it's going to be 1, 2, 3, 4. That means this alkene is going to be in the third position. So it's going to be but3N, just an En, and then 1-ol. So it's going to be but3-ene-1-ol, essentially. And then you're going to then have the 2-methyl as a prefix. 2-methyl but3-1-enol. And the hydroxy prefix comes into play here with this hydroxy group because this functional group is an amide and congests the suffix of the thing quite a bit. It's also the priority group over the alcohol, so you're going to have 1, 2, 3, 4. That's going to be butanamide, and you can't really add an ol in there, butanamide-ol. It just sounds a little bit weird. So you then add 1, 2, 3 hydroxy butanamide. If there was an alkene in this functional group somewhere, it would be butenamide, but because it isn't in this, there is no alkene or double bond in this group, it's anamide. So the little N or an has to specify between whether it's an alkene, alkane, or maybe even an alkyne if it's an incredibly complicated molecule. But yeah, that's it for this introduction to nomenclature and organic chemistry, and I hope you enjoyed it. I hope I explained it well. I think I did it better than when I did it like an hour ago when I tried to practice explaining it with this whole new little thing. I even discovered that you can use pens and stuff. It's all quite cool, and I hope you stay around for the rest of this series. With that, I recommend subscribing, and have a nice day.